Hello, today we're talking about simple machines, and more specifically in this first part we're just going to be looking at mechanical advantage primarily. So, six simple machines. There's the lever, the wheel and axle, and the pulley. There's also the inclined plane, the wedge, and a screw. Those are the six basic types. When you use a simple machine, you're going to exert a force, and then ideally that simple machine is going to move. When you apply a force through a distance, meaning you push something and you make it move, you do work. And work is equal to force times distance. You may remember that from topics in physics. So work is equal to force times distance. So when you use a simple machine, you do work. If we want to lift a heavy box up to the back of a truck, we could look at two ways of doing it. One, we could lift it straight up, and lift it vertically, and then into the box of the truck, which would require a lot of force. Or we could push it up a ramp, which would require less force. But now, when we lifted up the ramp, or when we lifted up the vertically, we're applying a great force, a large force, but a small distance. And when we push it up the ramp, we're applying a small force for a larger distance. So it all works out. Um, and that's pretty much what that slide says. So here again, we're looking at the same amount of work, doing it either way, ideally. Large force, small distance, and here we have small force, large distance. But since work is force times distance, we would end up with the same amount of work. Now, in the real world, we're going to lose some of our effectiveness because we're going to have to overcome what force is going to be a problem for us pushing it up the ramp, especially if we don't have wheels. It is going to be friction. So friction is going to make us do a little extra work pushing it up the ramp in the real world. On your equation sheet, which hopefully you've got printed off, this is the page that we're going to be focusing on in this unit. The work equation is previous in the equation sheet, but this is really what we're looking at. IMA, AMA, it gives you the different types of levers, and talks about screws and that sort of thing. So that's really what we'll be focusing on this unit. So since we've got two forces whenever we use a simple machine, such as a lever or a wheel and axle or a pulley or whatever, there's the effort force. That's the force that you apply to the machine, and there's the resistance force, which is the force applied by the machine to the output. Typically, this is going to be the weight of an object that you're trying to lift. We'll just try to keep it simple, but not always. It's the force that comes out of the lever. So phi and fur. Okay? And whenever we use a lever to lift something up, not only do we have the phi and fur, we've got the d and the dir. There's the distance that the effort moved. This was how far, if your hand was right here, how far your hand pushed the lever down. Okay? And then the distance of the resistance is how far the box, in this case, lifted up. The resistance lifted up. So we've got phi, fur, d, and dir. Mechanical advantage, usually we use a machine to gain what's called mechanical advantage. And the mechanical advantage is a number that tells you about how much less force that you're going to have to use to lift an object. So if we've got a mechanical advantage of 5, what that means is we're going to be using 1/5 the force to lift that object. It gives us an advantage and multiplies our input force by 5. So here you can see we're lifting a 100-pound rock, but with this lever we're only having to put 1/5 of that, or 20 pounds of force, into it. There is a trade-off, as there always is. Whenever we gain force, the trade-off is we lose distance. That's so that the work in and the work out are equal. So when we move our side of the lever down 5 feet, the load only lifts up 1/5, or 1 foot in this case. So that's an example of mechanical advantage. So again, just kind of reiterating a point, if we gain force, you don't get something for nothing. There's got to be a trade-off. And since we gain force, what we're going to do is we're going to lose distance. And whenever you gain force, you lose distance. And the reverse happens. If you lose force, you gain distance. So we can change the mechanical advantage of a lever simply by moving the fulcrum. So here we've got a mechanical advantage of 2. Notice that my input force is multiplied by 2. So I put 5 newtons in and I lift a 10 newton object. So if we move the fulcrum a little closer to the resistance, then my mechanical advantage goes up. It goes up from 2 to 3. Okay. There's two basic types of mechanical advantage. There's the ideal mechanical advantage, which is IMA, and the actual mechanical advantage, which we'll refer to as AMA. The ideal mechanical advantage is what you should get if there was no friction. If it was a perfect machine, this is the mechanical advantage you would get. The actual mechanical advantage is what you measurably get. So this includes friction, and these two in the real world are never going to be the same. Which one is going to be greater? Think about it. The ideal mechanical advantage is going to be greater than the actual mechanical advantage in the real world. So this is an equation that's on your equation sheet. This is the equation for ideal mechanical advantage, IMA. This is simply based on the distances between, for a lever, it's the distance between the fulcrum and either where you're pushing or where you've got the object you're trying to lift. And these distances are given out on your equation sheet too to help you figure those out. So it's d over dir. And again, I'm not going to make you memorize these equations. You're gonna have your equation sheet. The actual mechanical advantage, this is what you actually get, and this includes friction that's taken into account. This is Fr over phi, and Fr is the resistance force, and phi is the effort force. So it's the weight of the object you're lifting divided by how hard you're having to push or pull to do that. I want you to make a note on your equation sheet with this slide and I'll tell you what to write down in just a second. For an ideal machine, your actual mechanical advantage equals your ideal mechanical advantage, meaning you actually get what you ideally should get. And this never happens, but allows us to do some predictory. I'm not sure if that's a real word. Predictory allows us to predict what we should get out of a machine. So setting your AMA equal to IMA, Fr over phi equals dir over d, and cross multiplying, phi d equals Fr dir. So next to your AMA and your IMA equations, what I want you to do is I want you to write this equation, phi d equals Fr dir, and put for an ideal machine. So phi d equals Fr dir for an ideal machine. And I'll let you use that, well, I guess I really don't have a way of stopping you from using it at home, but I'll let you use that on your test. So phi d equals Fr dir. So if the mechanical advantage is greater than 1, okay, what that means is that it's making it easier to lift the object. So you have a small effort force. You don't have to push very hard. Okay? And the trade-off is, though, that you have to push your side quite a bit further than the object is going to lift up or whatever is happening. The resistance is going to move. So that's mechanical advantage of greater than 1, 1.2, 3, etc., etc. Okay. If I move this fulcrum over to the left, okay, I'm going to get a mechanical advantage that's less than 1, which means now I have to push harder than the object weighs. Now why would I want to push harder than the object weighs? Well, I still get an advantage. The fact that I don't have to push my side very far. If I move this side down a little bit, my effort distance is small. My resistance, my dir, is going to be much bigger. So that is less than 1. Mechanical advantage is less than 1. So now if you put the fulcrum right in the middle, your mechanical advantage is equal to 1, and basically nothing changes. Your effort force is the same as the weight of the object, the resistance force, and your distances don't change either. Mechanical advantage can never be negative or 0. It's always going to have some actual number. It might be really, really small, and in the case of screws, it'll be really, really big, but it'll never be 0. Okay, and we'll stop here for this one.